Good morning, everybody. As Shannon mentioned, this is Raja Devata. I'm Senior Technical Specialist at Altair, and I have been with Altair for past 6 months. I'm located in Boston. Today, I would like to speak about one of the interesting features in Feko. This is one of the new features that we have kept very huge efforts into this particular solver, that is Faceted UTD solver in Feko. We are going to talk about that particular thing in this particular very short session. And the outline of this particular session is I would like to give a glimpse of CEM solver overview, and then come to the UTD solvers, outline of UTD solvers broadly. I would really like to discuss about that particular part. Then I will be streaming down into the Faceted UTD solver. That is the topic of interest for today. I will come there and we'll talk about some snippets or the highlights of Faceted UTD solver. After that, I will give you a brief demo of how to use this particular solver. Yeah, most of you already aware of this particular thing. We do have a strong solver portfolio of solvers in Feko that can accommodate to solve broad range of electromagnetic problems. Yeah, we have full wave solvers, and also we do have asymptotic methods and stuff like that. We can hybridize them appropriately to solve the electrically large problems, especially. That's where the hybridization helps us. In that particular asymptotic solvers, if you see that physical optics and relaunching geometric optics, and of course the UTD and faceted UTD solvers. Yeah, where these particular solvers are very efficient for electrically large problems and can provide the results in reasonable computational resources and time. That's where the whole point of using this asymptotic solvers. And then UTD is a uniform theory of diffraction, and FUTD is a faceted uniform theory of diffraction. And how are we going to use this particular solvers? Of course, in that particular demo, you will be seeing that particular part. All the asymptotic solvers we are going to apply per phase. Of course, we will, when we are going to do the demo, I'm going to take an helicopter model, and we can see where we are going to apply this particular solver. Yeah, whether it may be UTD or faceted UTD, we are going to apply per phase. I'm just calling it as UTD, both the things as UTD for now. Yeah, once we distinguish it, we can come down there. Then just a brief information about facet uniform theory of diffraction. As I mentioned, all the asymptotic solvers are very efficient for electrically large and complex problems. Similarly, uniform theory of diffraction is formulated for modeling electrically extremely large structures where physical optics and relaunching geometric optics may not be of much help. Especially there, this particular solver will be of help to solve the problems. And it is extremely large with respect to wavelength. Yes, that is one important point with respect to the wavelength. It is extremely large, and also it can consider many effects like diffractions and creeping waves, reflections, multiple interactions involving reflections and diffractions. All these things are considered when we are solving. We can select those settings when we solve this particular problem using this particular solver. And as I told you, UTD may be suitable, and it is mainly based on field ray tracing as opposed to launching. That is the unique difference between ray launching geometric optics and uniform theory of diffraction. Yeah, actually, uniform theory of diffraction is basically formulated into two UTD solvers. One is the UTD solver, and other one is the faceted UTD solver. UTD, the plain UTD, just a simple UTD method, I can call it as, just to distinguish between the UTD and faceted UTD. For the case of simple UTD, it is going to be applicable only for the flat plates and cylinders. And that's where the whole formulation was made for the simple UTD solver. If you have any arbitrary shape or something like that, plain UTD may not be of much help, and it can't able to solve the problem. And this is where and also it is going to be accurate method of moments is hybridized with the UTD to solve the problems. And one more interesting thing is using this particular UTD based version of the solvers is it is mainly independent of the frequency, whether you solve the problem with 1 gigahertz or 10 gigahertz or 100 gigahertz, your compute resources won't change. They are still the same. That is a huge gain when you are trying to use this particular solver to solve the problems. And also, as I mentioned earlier, this solver can accommodate all the multiple reflections and edge or wedge and corner diffractions and creeping wave effects. All these things are supported for this particular case. And you can see over here a simple ship geometry where we could able to mount a X-band radar, and we simulated it, and you can look into the radiation pattern of this particular problem. Okay. Then I'm going to jump on to the faceted version of the UTD. We just now saw the simple UTD solver. Now we are going to talk about faceted version. You can see in the older, that's what they are calling it as old UTD solver. I'm calling it as simple. That's fine. Where you can see only flat plates and an antenna is placed on top of this particular chip model. And we could able to solve all those things. And also you can see the corner diffractions and edge diffractions and reflections and everything. Where we also solve this particular problem with method of moments and hybridize it with UTD. Okay, that's the representation of the old UTD solver. And now you can see over here the faceted UTD solver, where you have a very arbitrary shape, a automobile vehicle I have taken over here to solve the problem, and we could able to mesh it using UTD, and we could able to solve that particular problem. Yes, again, same thing. Faceted solver is also helpful in solving the electrically large problems, and also especially for the antenna placement applications at very high frequencies. And also, if the mesh is based on the triangular mesh versus polygonal plates. That is the difference between these two solvers. And very memory and runtime efficient, and they are independent of frequency. You can see in the upcoming slides how good they are. And as I mentioned, with the simple UTD solver, these are also going to consider the multiple reflections, diffractions, and creeping waves. All these things can be considered when you are solving this particular problem. And this particular method goes very well with the equivalent sources. The combination of using the equivalent sources of equivalent source radiation pattern of an antenna with the automobile vehicle or any platform works very, very well. Of course, in the demo part again, I will show that particular thing. Yeah, this is how you are going to select your UTD settings or faceted UTD settings. You can see over here, if you go to the UTD settings, there you can see under the ray contributions over here. You can select for the advanced, then you can get the faceted UTD settings where you can select direct field, surface reflection, corner and tip diffraction, creeping waves, edge and wedge diffraction, and higher order effects. All these things can be considered when you are trying to solve the problem with faceted UTD hybridized with method of moments. Okay. And it is also hybridized with the method of moment, both the coupled and uncoupled cases. That is the huge add for this particular solver as well. And this is one of the simple problem that we solved, which is considering the rays contributing to the far field pattern at each angle. You can see the rays which are diffracting, reflecting, all the phenomena is considered to contribute to the far field pattern of the antenna that is mounted on a ship. Okay, let me jump onto the demo and let us come back to this particular slide and we will discuss about that particular part. Before going to the demo, I would like to show some important information regarding the solver, about this particular solver, and how to get the information from the documentation. Because so far, because this is only a brief session, we may not able to cover the entire things. That's why what I always suggest is please go to the documentation, open the user guide, And you can look into the faceted UTD solver over here in this particular user guide. Okay, and get more information regarding this particular solver. And I'm going to go to the, you see, I'm just streamlining everything and I'm going there. You can find all the relevant information regarding the uniform theory of diffraction in detail over here. Okay, whatever I discussed over here, and also how to apply. Also, this is available over here. Just go to the user guide and look into it. And also, we mentioned where this particular faceted UTD solver is applicable. You can see method of moments UTD. Yes, same thing is applicable. Okay. You can have a sneak peek of the user documentation so that you can get a feel of this particular solver. Let me get back to the demo part. I'm opening my launcher again. I would like to open the CAD Feko session. Basically, in this particular thing, I would like to take a helicopter model and take a blade antenna that is mounted on top of a helicopter model. I think like this, I'm going to simulate the same kind of problem over here in our demo part. First, what I would like to do is I would like to take a blade antenna. As I already mentioned, that UTD faceted UTD solver works very well with the equivalent sources or the implicit sources. That's why I would like to capture the equivalent source pattern of an antenna. Okay, let me jump on, go to the create new project. Of course, I would like to go and use a component library feature, which is very handy for setting up the antennas, bringing the antennas and the platforms into the CAD Feko, so that we don't need to struggle with what I can call designing these antennas from the scratch. I had my blade antenna. Let me take that particular thing. I would like to use this particular thing at 1 gigahertz. Of course, I would like to solve this particular thing using method of moments. Then I will take this single frequency. For the time being, I don't want to align anything. Just deactivate that particular thing, add to model. Basically, what I'm trying to do is I'm trying to capture the far field radiation pattern of this particular blade antenna. That was my goal, so that I will be having the data so that it can speed up my computation as well. Okay, you can choose export fields to ASCII file, okay, FFE file. Click apply and click OK. Let me save it, file, save as, and I would like to go to the create a folder for the Fireside chat series, Faceted UTD demo. That's what I would like to keep. And I know this is a blade antenna. I would like to give a blade antenna for this one. And then I'm just jump onto the Feko solver part and I can solve this particular thing. It will be very fast, and we could able to look into the folder and try to get the what I can call far field radiation pattern. You see, I just simulated this one. I would like to use this particular thing. I would like to have a sneak peek of this particular thing so that whether I get all the values and stuff like that. Okay, you see over here, everything is available. Instead of using the real antenna, I would like to use the far field pattern of this particular data, okay, into my faceted UTD solver. That is the first part of the blade antenna part is done. Now we need to mount this radiation pattern on top of the helicopter. That's what I will do now. Open this one. And let me go to the new project and open a plane. I'm going to take a helicopter instead of plane. We have a platform model available. I would like to bring the antenna model into here. Click OK. One small thing I would like to do is, because we do have a automatic meshing is turned on, I would like to deactivate that one so that it won't do anything for us for this particular thing. Next thing is I need to mount my antenna on top of this particular helicopter. I already had my blade antenna pattern is available in the data format. I would like to use that particular data as an equivalent source. First thing is I need to bring that one over here. I need to define the far field pattern. Okay. I need to bring that one, browse. Then I would like to go there, Faceted UTD demo, and I have the pattern available. I know that the number of data points that I got are 37 and 73. Also, we can have is look into that where to get that particular thing. Yes, I tagged them. I got the data available now. I would like to place somewhere over here on top of this particular helicopter. Okay, let me go there. Source or load tab, and I would like to bring the far field source. I need to change the work plane so that I can mount it on top of the, because it by default comes at the origin. I want it on top of the helicopter. Okay, this is where I want to have it. I just would like to add a little bit of just above the ground plane. And then I just want to tweak it so that it will become simple. Okay. And also I would like to offset this particular thing on the far field pattern when I would like to compute. Now I would like to, I had my antenna available, I have my plane is available. I need to assign the faceted UTD solver on the helicopter. I will choose that. I already discussed that we are going to apply this particular faceted UTD solver onto the faces. I'm going to select all the faces of the helicopter, and I would like to assign this particular faceted UTD solver to the faces. I'm going to go to the solution and then go to the faceted UTD solver. Okay, apply, click OK. And that means I'm going to solve this particular problem with faceted UTD solver for the plane, and antenna I'm going to use method of moments. Okay, I know the frequency part is 1 gigahertz. That's where my blade antenna is working. I'm going to apply. And the next part is I need to request the far field pattern of this particular configuration. Okay, only one thing is I need to tweak my work plane, otherwise it will be at the origin. Okay, I would like to bring that one from here. Okay, it is available in the far field source, the work plane. That's where we tweaked it. I would like to tweak that one. 2.2, 5.5. The offset parameters that are there. Create, apply, okay. And after that, I would like to save this one. Save as helicopter with helicopter Faceted UTD. Okay. And all the settings can be available. We can look into the settings, go to the solver settings and look into the high frequency. You can find all the settings over here for the UTD. Okay, I go to the advanced tab and you can see the settings for the faceted UTD. Okay, I'm not going to touch anything for now. We can play with that one. And just I will hit the Feko solver button. Okay, it is going to save and it's going to run the problem now. Probably it will take like less than a minute or so to finish this particular thing. Yes, we'll just hang on to this one. And let us go back to this particular thing. And I would like to see over here, if we would like to solve this particular problem with UTD solver, we can able to solve using MLFMM. It will take like 14 hours to solve the problem. Whereas if we wanted to solve the problem with this particular faceted UTD solver, at 1 gigahertz, it is going to take only 8.7 seconds. Similarly, it may be 10 gigahertz or 100 gigahertz or 500 gigahertz. We can solve this particular problem. But whereas if we can take any of the full wave solvers, we can't even think of solving those problems. Especially that is one of the answer for the questions is this one, where we can have an answer where we don't have an answer with the full wave solvers or some of the asymptotic solvers. Faceted UTD can give you some light for the solving those EM problems. And again, this is an asymptotic solver. Yeah, the accuracy, definitely we need to compromise on that particular thing. but at least we have an answer for our problem. That is the biggest asset of solving the problem. And yeah, same thing we solved with the 1 gigahertz, 2 gigahertz. You can see over here. Similarly, you can see over here for faceted UTD 1 gigahertz and 2 gigahertz. It is taking the runtime same, and it is runtime and resources are frequency independent. That is the main thing. Let me go back to the solver and see. Okay, we're able to finish this one. I would like to quickly go to the post FICO and plot the radiation pattern of this particular problem. And you can see over here. And also, I would like to make it a little bit opaque. Okay, you can see this one, and we can look into our out file requirements, computational requirements. It took approximately 153 seconds, okay, on this particular machine, and 257 megabytes. Okay, that's how quick we could able to do this particular, like 3 minutes it took. I was including all the diffractions and all. If we don't, yeah, it will be super fast. Yeah, this is a quick demo of a faceted UTD solver and a glimpse of faceted UTD solver.